Okay, so this is the final lecture in MEC 5804 at Carleton University. We will be talking today about everything a reactor engineer needs to know about nickel alloys. So I'm going to minimize the Skype screen here and go straight on to the lecture. I'm in full screen mode here, sharing this full screen with my Skype participants. So, oh, by the way, I've probably shown this slide every time. You're probably wondering what this photograph is. For those of you who are not familiar with it, that's Chalk River Nuclear Laboratories. That's where I spent most of my life. So nickel alloys are probably one of the more enigmatic alloys that are used in a nuclear reactor core. When reactors were built, nickel alloys were very popular for certain specialized components, especially springs. So they're standard alloy and they're standard purposes, as I say, especially for spring material. A very good spring material, especially the precipitation hardened nickel alloys, and we'll talk about that in a minute. But when people put these components in reactors, they really had no appreciation or didn't think through about what long-term operation in a nuclear reactor core, especially a reactor core with a high thermal neutron flux, what that does to nickel alloys. So there were some classic papers that came out in the 80s, the early to mid 80s, principally by a guy called Larry Greenwood. And Larry showed that nickel in particular, if it's in the reactor core for long enough, can have a very significant effect. There can be a very significant effect of the radiation on nickel alloy components if they're in the reactor for long enough. So that is one thing that I want to talk about in this lecture, but also other aspects of about nickel alloys and things that you might need to know if you're a reactor engineer. So what I've got here is a ternary phase diagram at around about 400 degrees C. Nice if it was 300 degrees C, but this is 400 degrees C. I think it's the only one that was available. I don't know why people pick 400 degrees C, but it's a reasonable temperature to look at. It's a slice through the ternary phase diagram, chromium, iron, and nickel. And it shows the relative composition or the approximate composition for the different alloys that are used in nuclear reactors. Now on this phase diagram, the areas marked out in blue denote alloys which are primarily gamma phase alloys. So they're primarily, other than a few precipitates, their main phase is their single phase alloys. And the gamma in this case refers to the FCC phase. Now this is distinct from iron alloys, and we talked about this last week when we talked about steels. Iron alloys are primarily, or what we would call low alloy steels, if they're iron with carbon in them, they're alpha phase, and the alpha phase means it's a body center cubic. There are these intermediate phases which are a mixture of alpha and gamma, but typically when people are talking about steels, if the nickel composition is less than 28%, if we're in this region here, the material is often referred to as a steel, whereas if it's greater than 28%, it's referred to as a nickel alloy. So these are some typical nickel alloys that are in use or have been used in nuclear reactors. Alloy 800 is used in steam generators, more the later generation of steam generators. That's not in the core, which is good because it's not really good to have too much nickel in the core, especially if it's a major component. But in the steam generator, that's okay, and that's in the balance of plant. Pe16 and 706 are precipitation hardened or hardenable alloys which are used in fast reactors, in cladding and duct material. Now these alloys can be used in fast reactors because in fast reactors we don't have to be as concerned as we do in thermal reactors with the N-gamma production of nickel 59, which can have very serious consequences for high nickel alloys in thermal reactors, producing eventually a lot of helium. But in a fast reactor, as we've discussed in some of our earlier lectures talking about radiation damage, in the fast reactors that's not a big concern. So nickel alloys had a number of useful properties, relatively low swelling compared to steels. I think that was probably the main one, why they were used in some of the early fast breeder reactors. So fast reactors do use nickel alloys. I'm not sure current fast reactors which are operating, I think only in India, perhaps in Japan, and in Russia, Bor 60. I'm not sure what components they have. The Pe16 and the 706 here, Pe16 was used in the English, British fast reactors, Dounreay fast reactor, and the PFR, and the 706 was used in the French Phoenix, Super Phoenix reactors for fuel cladding. Okay, moving on. Inconel 718 is an alloy like X750. It's also precipitation. These are both precipitation hardenable materials, and we're going to talk about that in a minute. These are used, 718 and X750 are used in springs, but also in other special components where high strength, high ductility is required. Alloy 600 has a composition very similar to X750, except it doesn't have enough titanium or aluminum to form the precipitates that X750 has. And we'll talk about these ordered precipitates, the gamma prime, and what gives some nickel alloys their precipitation properties, but also the gamma prime, these precipitates, the gamma prime precipitate in particular, are what you get in super alloys. So, but generally, the super alloys generally refer to those alloys which contain a lot of gamma prime. Again, I'll talk about the gamma prime in a second. Alloy 600 tends to be used in steam generators, just like 800. But it was primarily used in some of the earlier steam generators in early reactors, but there were some heats of alloy 600 which didn't behave too well, so I think many operators now tend to stay clear of alloy 600. I think alloy 800 is a preferred, and alloy 690 are now the preferred steam generator materials. I think alloy 800 is used somewhere else, not quite sure. Alloy 625 is used in mostly for guide tubes, flux thimbles in PWRs, for instance, or the carrier rod material for flux detectors. You might mount flux detectors on a rod which is made of Inconel 625 or Inconel 600. So these materials you tend to see related to flux detector assemblies. Now, flux detector assemblies often they're usually interchangeable, and if they start to deteriorate after 4 or 5 years of service, they can be just changed. So even though it's known that Inconel becomes very brittle after a few years in a reactor, people still tended to use these materials in the reactors and just shrug their shoulders after 5 years when the things rattle themselves apart and say, oh well, we'll replace it and put a new one in. So 690 is used in steam generators. Hastelloy X is a high temperature nickel alloy. It's used for high temperature applications. There's another variant, I think, Hastelloy N, which is a slight Hastelloy N, I think, is somewhere around this region, but I don't have it on this diagram. Or it has too many. Hastelloy N has too many other elements to be on this ternary phase diagram. Hastelloy N is used in molten salt reactors. Hastelloy X is a candidate material for some of the high temperature gas reactors which are being planned for the Generation 4 program. Anyway, what I'm saying, I've restricted these ones to those alloys which contain perhaps 90% either iron, chrome, and nickel. And this composition is just taking their iron, chrome, and nickel and assuming that the alloy is 100% of one of these three. And therefore, these compositions there are based on the relative amount of iron, nickel, and chrome. Okay, I went on that, probably kept on that for a little bit too long. Okay, so you heard me talking about the precipitation hardening effect of nickel alloys. And this is what it's all about. And the most well-known and the most commonly used, or commonly utilized, I should say, precipitate in nickel alloys that are precipitation hardenable is the gamma prime. Now the gamma prime precipitate is illustrated here. If this is the FCC lattice for pure nickel, one can form precipitates of an ordered phase. And when they say ordered, this is an ordered phase here. You have the same crystal structure, but you substitute for the base material, your in this case nickel, you substitute another element. And typically this is aluminum, but it can be titanium, niobium, or tantalum. You can these are interchangeable. But you'll probably hear about nickel 3 aluminum if you're dealing with any superalloy applications. So in Inconel X750, that's used typically in engineering applications, some people might call it a superalloy because it's a nickel alloy that is good at high temperatures, but it really isn't classically a superalloy, because a superalloy, and if you remember some of the I talked about the physical metallurgy. I talked about this in one of the earlier lectures, either lecture 1 or 2. Alloys which exhibit what I would consider real superalloy properties, that is, their yield strength increases at high temperatures. These alloys contain a very large volume fraction, 70–80% of the gamma prime. In Inconel X750, we're talking about 10 or 15% gamma prime. So that volume fraction of precipitate, of the gamma prime precipitate, isn't sufficient to make the mechanical properties dominated by the gamma prime properties, but it is sufficient to create hardening centers which impede dislocation motion, and therefore give the nickel its high yield strength, or the Inconel X750 its high yield strength. If you remember again some of the earlier lectures, if we had a dislocation gliding through this ordered phase, you can well imagine, so this would be gliding on a 111, it would be a 111 direction, and typically on a 111 plane. 111 110 plane, this close packed plane here, you can see how when something that's gliding on that plane will, sorry, it's not on a one, I'm mixed up. It's a 110 direction. It's this direction on a 111 plane, which is the close packed plane, which I don't have identified here. It's along here and up here. This is kind of this triangle here. So the 110 slip on that plane, when you, if you like, you displace on this plane, I wish I'd drawn it now. If you displace one of these aluminum atoms into that site by the passage of a dislocation, it creates what's called an antiphase boundary. And on the plane, on the slip plane that we're talking about, the atoms are out of sync with all the other atoms in the ordered structure. And that creates a stacking fault. And so that means that it's harder. That makes it doubly hard for a dislocation to glide, because not only does it have to displace or shear through the atoms, but it also has to create a stacking fault. And that additional energy of creating that stacking fault, or antiphase boundary, we should say, it's normally classed as an antiphase boundary, that makes that material harder. So anyway, it's hard for dislocations to pass through this compared to this. It's as simple as that. So we're talking about slip on the 111 plane here, and the slip direction is 110. Okay, so sorry, I got off track a little bit. I'd remind you to maybe go back to lectures 1, 2, and 3, where I talk a little bit about this kind of process. Certainly talk about slip and close packing, and also antiphase boundaries. So another form of precipitate, which is typical in Inconel 718, is the gamma double prime. This is similar to nickel 3 aluminum. In this case, though, it's a body-centered tetragonal phase. So you don't have the same possibilities for what happens in a nickel superalloy, because that's an oddity of the gamma prime, what gives the superalloys their property. So it's something about the high temperature properties of dislocation motion in a gamma prime structure that gives them their properties. Being body-centered tetragonal, this would be like a body-centered cubic material. It would be very difficult then, just for slip in general. So this body-centered tetragonal gamma prime is just a hard phase. It's just a hard phase for any passage of any dislocations. So here's a periodic table to show you which elements in nickel tend to form these gamma prime or the gamma double prime precipitates, which make the material precipitation hardenable. So if you heat treat a nickel alloy which has enough aluminum, titanium, niobium, or tantalum in it, you can form precipitates which harden the material. Also, this shows typical constituents in nickel alloys, but also it shows that boron and carbon will segregate to grain boundaries. Now, carbon and maybe not so much boron. Boron actually is an addition to nickel alloys to make them more formable. I think it has to do with boron segregates to grain boundaries, and their grain boundary sliding is more feasible with this boron phase on the boundary at high temperatures, I think. But in the same vein, carbon is an addition with a heat-treated alloy that is sometimes preferable because the carbon forms carbides on grain boundaries, and these carbides on the grain boundaries prevent grain boundary sliding at high temperatures when you want creep resistant. You want to have high temperature creep resistant for the nickel alloys. So it's good to have carbon for that purpose. So on the one hand, boron may be added to make it material more deformable during processing. Carbon is produced, but it would be with a heat treatment after it's been fabricated to instill some high temperature creep resistant by forming carbides at the boundaries. Unfortunately, when you heat treat nickel alloys containing sufficient carbon, the nickel alloys contain chromium, and what happens is that the combination of the precipitation of the carbides on the boundaries, typically the carbon reacts with chromium to form chromium carbides. These are the M23C6 typically, and this formation creates a depleted zone of chromium, and chromium is in the alloys to give it good corrosion resistance. So you've got to be careful if you heat treat nickel alloys to a certain extent. The chrome creates carbides but is depleted at the boundaries, and then these boundaries are then subject to intergranular attack either by acids or just simply by corrosion. There'd be preferential corrosion along the grain boundaries now because you have this depleted layer of chromium, and that's what's called sensitization. You may have heard of that in your travels, that you can heat treat some nickel alloys with containing chrome, and the subsequent segregation of chromium carbides at boundaries depletes the chrome in the vicinity of the boundaries. And the solution to that is just keep heating, in fact, because then the remainder of the chromium in the bulk of the phase will diffuse into these depleted chromium phases once all the carbon's been used up. Okay? Some people think that the composition of the boundaries changes during irradiation. I'm not sure about that. You probably heard me talk sometimes about irradiation effects and thermal effects. Imagine you put a component in a reactor, it's in there for 20 years, maybe irradiate with a high or a low flux, who knows. And then people take it out and have a look at it and say, "Oh, look at this! What's happened? This has been subject to X amount of neutrons being neutron flux, neutron fluence, dose. It's been exposed to a certain amount of dose, and this has created so many displaced atoms. Blah blah blah." And they might attribute any changes they see to the neutrons, but ignoring the fact that it's been sat at temperature for 20 years. And the reason for that is that there's not much evidence or not much data available where somebody's taken some of these alloys, Inconel X750 as an example, or just any alloy, and actually sat it for 20 years at the same temperature you have in a nuclear reactor. Bearing in mind the nuclear reactor cores are typically operating between 250 and 350 degrees centigrade. So roughly around about 300 degrees centigrade. People don't have the experience often for the time temperature transition characteristics, or explore the time temperature transition characteristics of many engineering alloys, just simply sitting them there at temperature for many, many years at a given temperature. People don't have the luxury of having to do the experiment. You might remember this from some of the earlier lectures. How does the precipitation hardening work? Well, it works by these precipitates being barriers to dislocation motion. Now, the dislocations well, first off, this strengthens the material because it makes it harder for the dislocation to pass through the material. But dislocations can still pass through the material, albeit at a higher stress needed to cause the slip, by different mechanisms. One of them being cutting. It can simply cut through the precipitate, and what you would have is this antiphase boundary left behind. Once the dislocation has gone through, you're left with an antiphase boundary here. So in order to pass through that precipitate, create this antiphase boundary, that has taken extra energy, and that's what, as I say, is the essence of the impedance, because otherwise it's still an FCC phase. Why should it hold it up? Oh, there is one other factor. These gamma prime precipitates, they're typically a little bit different in volume. There's about 0.5% volume change, and that in itself actually is an impediment to dislocation motion, because dislocations, there'll be a certain energy needed to pass through a uniform strain field, and if you have regions of variations in the strain, that in itself creates an interaction, and you end up with some hardening for that. But that's a secondary effect compared to the antiphase boundary. The other way that precipitate dislocations can pass through is, well, not by passing through, but by going around and then creating this R1 loop. And have it in some of the earlier lecture notes. We didn't talk about the process that much, but you are aware of it. And these two processes, if you probably remember, I talked about precipitate size and aging and stuff like that. And there was in terms of the yield strength, if you were thinking about aging the material, when the precipitates are small, let's say you have a quenched material with lots of small precipitates, this would be the one mechanism that would be applied. But as the precipitates get larger, it's much harder for this mechanism to occur, because you're creating a much bigger area of antiphase boundary, primarily, and then this mechanism becomes more prevalent. And it's not that this looping is easier around big precipitates, it's that when the precipitates become big, they've aged, and by oswald ripening, that means that the spacing between the precipitates is bigger. And it's really the spacing between the precipitates which makes this looping possible. So when you get to overage system conditions, you're more likely to get, when the precipitates get bigger, you're more likely to get this R1 looping to happen. Of course, circumstances vary, and you may get a bit of each. As we see here, that depends on the particular stress state and the constraints in the material, and who knows what else is happening. And so even though precipitates, there are instances where you have precipitates that may have very similar size, like this and this, where in the one instance you see some precipitate cutting, in the other case you see some R1 looping. And this is what the R1 looping looks like. This is after dislocations pass through the material. It's left these loops around the precipitates. In some cases you get neither, and either because the stress is not high enough, or who knows, and you get this, the dislocations can't get through the precipitates or get around them, and they just get tangled up. And this is what structure looks like when you haven't had, either because the stress is not high enough, probably because the stress is not high enough, so you have some slip formation, and you just get the dislocations tangling up, and you're getting the material that starts to harden. But you haven't, at this point, you've got to that point where the stress is high enough to cause either this or this. And of course, once you get this tangle formation, that in itself will harden the material just from the forest interaction. I talked about carbides. One of the processes that are applied for nickel alloys that are destined for high temperature applications, such as turbines. Actually, I don't know, I'm guessing now, but I've read that precipitating carbides on grain boundaries is by design in some cases, where having carbides along the boundaries makes the material more resistant to high temperature creep by grain boundary sliding. So that's a very special kind of set of circumstances where the material might be operating at a very high temperature. And there is this mechanism of creep that can occur at very high temperatures. We've talked about diffusional creep in some of the earlier lectures, especially to do with ray theory and mass transport, diffusional mass transport. But this is now we're talking about the thermal mechanism where vacancies are the primary driving force for any diffusional creep. But in addition to diffusional creep being a high temperature application, this is outside of the realm of radiation damage now, there is this high temperature grain boundary sliding possibility. And this is where one grain will slide relative to another along a boundary. So precipitating carbides on the boundary actually limits that slip and makes it the material more resistant to grain boundary sliding at high temperature. But of course, what that does then is for a bog standard alloy operating at conventional temperatures, and let's say you're deforming it to the point of failure, and what happens is that you're deforming the whole material, you're hardening it, you're elevating the stress that you're subjecting the material, and eventually any material, just like you get in the neck region of a tensile specimen, it will eventually start to nucleate cavities. This is ductile separation at precipitates, inhomogeneities, and then you'll get microvoid coalescence. So what that means is this is the standard ductile failure mechanism that one would see in a standard tensile specimen, for instance. But because these carbides are all lined up along the grain boundary, eventually you might get failure, intergranular failure. So intergranular failure is often observed in nickel alloys when you have a lot of carbides along the boundary. And that's often sometimes mistaken for evidence of embrittlement. It kind of is in one sense, in that most of the deformation in this case now happens in a narrow zone here, as opposed to elsewhere in the matrix, in the material. But it's still a ductile failure. It's just ductile failure that's where you're getting most of the deformation, ductile deformation, occurring in the regions around carbides. And then it looks like an intergranular failure. But if you examine the surfaces of the fracture surface, you'll see this dimple. You'll see dimples, which would be the classic sign of a ductile failure mechanism. Okay, so you guys are well versed in this now. The whole object of this course is to focus on what reactor engineers need to know. And the main primary focus here is what reactor engineers need to know about building nuclear reactor cores. And nickel has a special place. It's unique in some to a large extent. And it's unique because of the nuclear reactions that are possible with nickel. So it's not unique, as in there are some other elements that have these peculiar properties, like sodium-22, for instance, is an isotope which is, I think sodium-22 is the product. It's equivalent to nickel-59. It's something that can be produced. I'm not quite sure whether sodium-22 is the parent or the daughter. I don't know. But anyway, sodium is also an element which behaves similar to nickel. But nickel is unique primarily because it's an engineering alloy. And so it's used in many alloys that are used in engineering applications. And we don't build many springs out of sodium alloys, so we don't really have to worry about it. But nickel is used heavily in industry, either as an addition or as the primary base material for certain alloys. But certainly most stainless steels have about 10% nickel in them. So we have to be aware of what radiation and long-term radiation does for nickel. I should have changed this. I'd like that to be a black one, but anyway. Remind you, we've shown you this before, conventional situation where we have radiation damage. How does it normally happen? By far the biggest contributor to displacement damage in nuclear reactors is the elastic displacement. What we have is an elastic collision between a fast neutron, high energy neutron, and an atom, and the energy transferred gives a kickback, a recoil if you like, and that creates multiple displacements and eventually many vacancies and displaced atoms, what's called interstitials, are produced from this one collision event. So in most reactor applications, about 95% of the damage, of the total amount of damage, nickel-59 aside, about 95% is produced by neutrons, fast neutrons with energy greater than 1 mega electron volt. Probably heard me talking about this before. And that's 95%, typically 90% of all the damage is created by neutrons with energy greater than 0.1 mega electron volt. And a tiny amount of damage would be created by this event from neutrons down to energies around about 600 eV. In the case of nickel, 600 eV is the minimum energy needed. If all the stars were aligned and it was a nice head-on collision, it was the minimum energy needed for a neutron to displace one atom of nickel. Of course, you wouldn't get this cascade, you just get one displacement. And of course, very little, because a 1 MeV neutron creating a collision cascade will displace something like 300 or 400 displaced atoms, Frenkel pairs. That's a 1 MeV neutron. A 600 eV, so that's 1 million electron volts, will produce hundreds of displaced atoms. 600 electron volt neutron will produce one. So in the early years of reactor production and construction and this kind of thing, often people quite rightly were only ever concerned with high energy neutrons, those that had energies greater than, let's say, 0.1 MeV, like hundreds of thousands of electron volts or millions of electron volts. And generally, often people made assessments of the material's ability to survive in a neutron environment based on the dose being measured in terms of well, how many fast neutrons would this material have been exposed to? Fast neutrons, let's say what neutrons greater than 1 MeV, because by and large that produces the vast amount of the damage, or the highest percentage of the damage. And often assessments were made based on these fast neutrons. And it really, in the last 20, 30 years, with the brilliance of Larry Greenwood, we've been able to realize, or people, researchers for sure, and now reactor engineers who've realized that some of their components in their reactor are turning to glass, have realized that there are other considerations, not just the fast neutrons, when it comes to damage in the material. So when you have a thermal neutron coming in, it can create a little bit of damage also, actually. So when I said 600 eV creates one damage, if you go to much lower energies, when it's thermal neutron, we're talking about less than 0.1 electron volts, very much smaller energies. The probability for a thermal neutron then to react with an atom actually increases. So you go through this a minimum in the reaction probability. And atoms can then react with thermal neutrons, just as you get with a fission process, for instance, absorb the thermal neutron and emit a gamma photon. This gamma photon has some energy and actually has a relativistic mass, and there is a subsequent recoil because this has momentum. Even though it's a photon, the atom has a opposite momentum, and what happens is that we get this, there'd be I guess a transition in the energy levels within the nucleus to form this gamma ray. But because the gamma ray is emitted, there's a recoil event associated with that. And that produces maybe about 4 or 5 displacements. So a 1 MeV elastic collision will produce hundreds of displacements. A 0.1 EV thermal neutron will produce about 5 or 6 displacements. And you think, well, that's good to know. So if you have a very high thermal neutron flux, there's something of damage is going to come from this kind of process. So you have to be aware of it. It becomes an issue for some steels, even ferritic steels. So when you talk about low alloy steels, not even nickel alloy steels, but low alloy steels, this can be a substantial fraction of the damage process. Now, neutron for neutron, for an iron atom, the efficiency of producing displacements is about a factor of 100 different. So if you had a flux, if you counted up all the neutrons with energy greater than 1 MeV and calculated how much damage you get from those neutrons, and you had the same number of neutrons with energy 0.1 EV and counted up all the damage from those neutrons, it's 2 orders of magnitude different for iron. For zirconium, which has a very low thermal neutron capture cross section, it's 3, 4 or 5 orders of magnitude different. So for zirconium, those fast neutron events are basically, to a large extent, to a first approximation, are all you have to worry about, ever. But when you've got iron, you have to worry a little bit. You have to include some of this in your damage calculations. Of course, if you're in a fast reactor, you don't have any thermal neutrons and you don't worry about it. Okay, so here comes the magic now. If you're nickel, the major isotope is nickel 58. It's about 68%. 69%. Lee can verify what the atomic percent is in the material. But this is the major isotope in nickel 58. And when a thermal neutron comes in, yeah, you're going to get this little recoil when it emits the gamma. But then that creates nickel 59. So when you have now nickel 59 here, the reaction with thermal neutrons, or the probability of reaction with thermal neutrons actually goes up. It's higher than it is for the on a per atom basis. It's higher than nickel 58. But also, with respect to thermal neutrons, you get these possibilities which are not possible for any other isotopes. Only nickel 59 has the possibility of absorbing a thermal neutron and emitting a proton, absorbing a thermal neutron and emitting an alpha particle. So when you do that in nickel 59, the alpha particle emission creates something like 1763 displacements. Of course, it's not going to be exactly that. It's going to be of the order of that amount. The NP reaction creates 222, and the N gamma is 5. In this case, the 5 is all for the recoil. In these cases, there's a small fraction of this number which comes from the damage created by these particles. So the recoil, most of these displacements occur because of the energy of the recoil, because an alpha particle is very much more massive than a proton, it's very much more massive than a gamma, even though relativistically corrected. So there you have it. You have all this possibility for a very much enhanced production of displacements when you have nickel 59. I'm just going to take a little side note here. So nickel 59 is only ever produced in a reactor, almost. The half-life of nickel 59 is 7,000 years, I think. So nickel 59 will eventually decay, and it has no natural abundance because it can only be created from nickel 58, which is the nearest stable isotope, naturally occurring isotope. Nickel 59 is not naturally occurring. It has to be created by some kind of absorption of a neutron. But there is some nickel 59 in the Earth's crust, created by neutrons either in natural reactors or from cosmic rays. So I guess some cosmic rays can also produce nickel 59. I'm not sure it's the same reaction. It may not be a neutron kind of reaction, maybe some other reaction. So, but nickel 59, there is a tiny amount of nickel 59 naturally occurring in the Earth's crust. And for that reason, I think it comes from cosmic rays. It's called a cosmogenic isotope. Just a little sideline. So what are we talking about in terms of the reaction probabilities? Here's the reaction cross-section in barns against neutron energy. So we have our neutron coming in, impacting on a nickel atom. And in the case of nickel 58, which is the most commonly occurring isotope, this is what the reaction cross-sections are for neutrons of given energies. So the probability that a neutron will, any neutron per square centimeter, what's the probability that it will react with any one atom? And this is given by this value, which is in units of barns, which is 10 to the minus 24 centimeters squared. So as I said, if you remember the lecture on radiation damage, you can think of the barn as an area. How much area does a neutron of a given energy, how much area does it see? How much interaction area does the atom present to it? So at very high energies, how much area does it present to it for a given reactions? So you can think of this as for certain reactions, right, sorry, it's just dependent on the energy without getting into the physics. So at very high energies for the naturally occurring nickel atom, this is 10 MeV, 10 million electron volts. For very high energies, you can get this N-alpha reaction, which would produce a lot of damage because even if it was a high energy neutron, you got a double whammy. You've got it would be absorbed, and that absorption will excite the nickel 59, but also will create nickel 59, but it will also the nickel 59 itself will spontaneously emit an alpha particle. So that's this for the reaction with a nickel 58 atom. The NP reaction is shown here. So again, they're only at high energies. And then the N gamma reaction, because gamma rays absorption generally happens at low neutron energies. So the gamma ray cross section, you've got a resonance region here, and then after the resonance area, typically the reaction cross section for gammas, for producing the N gammas, producing the gammas with the N gamma reaction, this reaction cross section goes up as you get to lower and lower neutron energies. I'm not sure that, I don't know where we'll see a spectrum anyway, so you'll see how relevant this is. So as you get to a lower and lower energies, the more likely it is that you'll get a reaction between a low energy neutron and the nickel 58. So for comparison, I put on this plot the nickel 59 cross section, but I've scaled it by 0.04. And 0.04 in this particular case is the steady state concentration of nickel 59 relative to nickel 58 in a Candu reactor core. And you get to this point after about 3 or 4 years of reactor operation. So in the peak flux part of the core, because the Candu reactor core has such a high thermal neutron spectrum, such a high thermal neutron flux, you can produce a lot of nickel 59 very quickly. And so after about 5 years of reactor operation, you get about 4% nickel 59 produced. So even if I've scaled by 4% the nickel 59 cross section for different reactions, N alpha, NP, and N gamma, shown here, it's still comparable with the naturally occurring nickel 58. So on a per atom basis, whether it's nickel 59 or nickel 58, this plot represents the relative weighting that one would give per atom for the different reactions. And so the important thing here, the N gamma is about the same. So, per nickel 58 atom or per nickel 59 atom, you'll get about the same amount of displacements for a thermal neutron from the M-gamma reaction once the nickel-59 has got up to its steady state concentration. And this steady state concentration exists because, and we didn't go into that, I don't think, because you're burning in the nickel-59, but then it has this, you're producing nickel-59 at one rate, and then you're depleting it. That's those equations. Oh yeah, you should know that, because that's the essence of the equations we talked about for the isotope production. It's being burnt out at a different rate. And so there's a point in time where you reach a maximum. And that maximum will be fixed if the nickel-58 concentration is limitless, if it's always the same. But the nickel-58 itself will be depleted eventually. So maybe after 100 years in a reactor, this will drop down to about 0.3%. Sorry, 3%, something like that. Anyway, it reaches a maximum very quickly and then dies off very slowly. Okay, so once we've scaled for the production, so we've taken a snapshot in time, we're 5 years into operation in a CANDU reactor, and this is the amount of nickel-59 we have. So from this nickel-59, how much helium are we producing? How many hydrogen atoms are we producing? Well, we use these numbers here. And as you can see, at 5 years of operation, the nickel-59 with these neutrons is producing a lot of alphas and gammas, and protons, comparable to what you would get in the naturally occurring isotope at the high energies. So if we didn't have many thermal neutrons, it wouldn't be a problem. Or, but what you'll see if I have it next, oh yeah, cross-section now. What we have though is this is a PWR reactor now. What we tend to have, because it's a power reactor, we tend to have a lot of neutrons down at these low energy range. And for that reason, we can produce a lot of, in this case, helium. I've just put on this 0.4% weighting for the nickel-59 reaction cross-section here. And what you'll see here is that when you have a spectrum like this for a PWR, when we have nickel-59 produced, I should have maybe used a CANDU in this case, when we have the nickel-59 produced, then we have this possibility then of producing a lot of helium. The high energy N-alpha helium production for the naturally occurring isotopes, they tend to be dropping off at the point where we're just at the edge of the energy range for a thermal reactor. So, and even for EBR2, for instance. So in EBR2, this is EBR2 spectrum. For experiments in the EBR2, there wouldn't have been too much helium to worry about. But there's a reactor in Russia where people have a lot of experiments, and this is the Bohr 60 reactor. And depending on where you were, which site you're at, which irradiation site you were in the Bohr 60 reactor, even though, well, first off, you don't have any thermal neutrons here to react to give you the nickel-59, or many to react to give you the nickel-59. But you have a lot of high energy neutrons to react with the naturally occurring isotopes, nickel-58, iron-54, chrome-50. These are the most abundant isotopes. And so you can get you can get helium produced when the energy in the fast reactor is high enough. I was going to go back a little bit. Yeah, so this is dropping down here at around about 10,000 EV. Yeah. Oh, well, this tail here, we might be producing some nickel 59 also. Yeah. So there we have a cross section of 0.01. And at that point, we have a flux of a flux here, sorry, of 10 to the 13. So even in a fast reactor, we may still get some nickel 59 produced. And we have this possibility then, if you're producing a little bit of nickel 59, then once you've got the nickel 59 produced, you've got this possibility reaction here. Oh, you've got a resonance here. So you've also got, you might actually also produce a reasonable amount of helium, even in a fast reactor. So by and large, you get less, but you still have this possibility both at the high energy range and the low energy range, especially if you're talking about a Bohr 60 reactor, to produce helium. And I guess the thing to do is put a spectrum in the spectra of Bohr 60 or EBR2, any fast reactor, and I have them, I think, in the file. Anyway, I have these spectra. If you care to do it, it's something I just made a mental note. I should try that at some point and see how much helium is being produced by these, both by the naturally occurring route, but also the nickel 59 route. Nickel 59 would come from here. Okay, moving on now. So it's just some interesting little exercises that one could consider. So actually, before I leave this, I should say that, again, people make generalities. People working on materials engineers, reactor engineers say, "Oh, it's a fast reactor. We don't have to worry about it. We don't have to worry about it because we don't have any thermal neutrons. We don't have to worry about helium production." But really, they're often ignoring the fact that, yeah, you're getting a little bit of this kind of helium production, but also there's enough low energy neutrons here to also contribute to the helium production. So it's not zero. Okay, so nickel. How did I get into nickel? OPREX from irradiation facilities and test reactors. Nickel alloys are fascinating. So here's an irradiation effect on the mechanical properties of Inconel 718. So Inconel 718 is like Inconel X750. It contains the gamma prime precipitates, but it also contains those body-centered tetragonal gamma double prime precipitates. So it's a double precipitation hardened alloy. And as I said, these precipitation processes and the creation of these precipitates make these alloys very good for springs, because that raises their yield point, and they're good spring material. So what happens when you irradiate them? So this is a stress strain curve after different doses. There's unirradiated, and this is a low dose, and this is the Inconel 718. In terms of the engineering stress strain curve, the irradiation doesn't really lower the strength much. It just simply becomes more brittle, less ductile. Anyway, so the radiation effect, any radiation hardening you get, oh, actually, if anyway, it's not as apparent. So even though you might be creating some dislocation loops and stuff like that, some clusters, the fact that it's already hardened from the precipitates means that any additional hardening from the radiation, you barely notice it. If it's solution annealed, so basically all the material is in solution, there are no precipitates in the material, the yield point is very much lower, but also you can harden the material with irradiation. So when you create dislocation loops and hardening centers from the clustering of the point defects, you do harden the material. And that's concomitant with the hardening, of course, is the reduction in the ductility. So that's one interesting thing about solution annealed, precipitation hardened annealed materials. There's another effect of irradiation on the mechanical properties, and that has to do with the gamma prime phase itself. So two things happen. The gamma prime phase is ordered, and this is an electron diffraction pattern showing these points here correspond with the intensity, if you like, corresponds with the volume fraction of the ordered phase. And after you irradiate, this is relatively low dose, 3.5 dPa. A lot of this volume fraction of the ordered phase is starting to decrease. And then you go to a further point, you get to a minimum. And this minimum may be this balance because the precipitates are being disordered. But thermally, you're also at, what temperature are we at? 288 degrees centigrade. There is the thermodynamics is also acting in the opposite direction to order the phase. So radiation damage may be dispersing and mixing up the material just simply by ballistic mixing. At the same time, you've got the thermodynamics acting and the material wants to reorder. So you'll get to some minimum point where the two processes are balancing one another. So you end up with a little bit of gamma prime after a high dose. So not only radiation is taking away this ordering effect, so you essentially losing the hardening that comes about from having this ordered solid solution. There's another factor, is the compositional, you have this ordered solid solution, this ordered precipitate comes about because you have a concentration of nickel and, of aluminum and titanium concentrated at one point, or in this case, when it's gamma double prime, niobium and tantalum as well. So you have some increased composition, but this also gets dispersed. So you remember I mentioned that there was another feature of the precipitation which imparts some hardening effect, and that is the fact that these ordered phase also have a different elastic modulus, there's some strain associated with them. And this is simply because you've concentrated elements, 25% in this case, of the material is aluminum in this zone. And that 25% changes the lattice, and that also makes it harder for a dislocation to pass through, in addition to the ordering. So you have two things imparting strength. So there's two things that go on during radiation. One is that this ordering stuff goes away, And then the second is that you get this dispersion. So both, in effect, soften the material. So when you look at the hardness of the material, when it's precipitation hardened, this hardness drops off. And you only see it at relatively low temperatures, because at high temperatures, it doesn't really matter. The unirradiated and the irradiated are the same. And that's where, at high temperatures, in effect, the material doesn't know it's been irradiated. It's the thermodynamics is governed primarily by all the vacancies that are created, the thermal vacancies which are created at the high temperatures. So from a diffusional point of view, the material, it could care less whether it's been irradiated here or not. And at this point, you'll have thermodynamically also, you will have all of this. You'll have gone back to creating, because diffusion is so much quicker at the high temperatures, thermal diffusion is so much quicker, the material can reform the gamma prime phase. So there's no difference. The hardness drops anyway because that's what happens at high temperatures. The material becomes softer. Interesting. So, what does it all amount to when you look at the mechanical properties of an alloy that's in use? In this case, this is some material that was at the Los Alamos facility. There was a special accelerator production of tritium. So they have this multi-hundred mega electron volt proton beam comes smashing down onto targets, and I'm not sure what the targets are, but these targets are used to produce tritium for some other reason. So it's accelerator production of tritium, and this is held in some kind of vacuum, I guess, and the device where these targets are sitting, it has you fire these high energy protons through what's called a window, and the window is actually a solid material, but of course the protons are high energy, they're going to whip right through it. And there's also a thing called a water degrader, which is housed by Inconel X718, and that's to slow the protons down enough that you get the optimum energy range for the reaction you want. So this is high energy high energy physics. So I'm not even going to get into it. I'm just guessing about what happens. All I know is that they have these what's called a water degrader, but also the window, the device, the encapsulation for the device where the targets are held. And the material of choice when these things were made was Inconel 718. So they put this material in there, and they noticed that after some years of operation, that it was degrading. So the two things they did, they had some test specimens in there to look at the change in the mechanical properties in order to assess at what point they have to worry about the structure. So it's like surveillance samples. They had some surveillance samples that they whacked with a certain dose, and then they this is actually material from the windows. This is not surveillance samples, sorry. This is material from the window where they've estimated what the dose is in terms of displaced atoms. And then they've done the stress strain curve. So not DPA, Inconel 718, high yield point, very ductile, bing, not bad. Low dose, that's DPA now in this accelerator configuration, 10 DPA, 20 DPA. That's basically failing in the elastic region. So basically really brittle. And also we're dropping down here. The ultimate tensile strength is going down. So that's one thing. It's being embrittled. But more importantly, the point where it fails, the ultimate tensile strength of that material is actually decreasing. It's actually lower than the unirradiated material. It's going down here. And I'll show you later with the Inconel X750 and Canada reactors, we're going down this curve. So two interesting things. One is embrittlement, and the other one is the yield strength. So if you look at the yield strength now, and these strengths, I think this was performed with little mini tensiles, I'm guessing. Unfortunately, the yield strength, I think in this case, again, I think the testing in this case was at room temperature. And I think at this case was also room temperature. But the irradiation was at different temperatures. So these are mechanical properties. I forgot to put that on the slide. I'm sorry. These are room temperature tests. And I'll correct that if necessary later on with a follow-up. But I'm pretty sure these are room temperature tests, different irradiation temperatures. So the interesting thing in general with these precipitation hardened alloys is that you get an increase in strength with increasing dose because you're hardening the material. But just like I showed you previously, it actually gets softer eventually. Sorry, not this one. There's not much difference in the precipitation hardened case. But in fact, you do get some hardening. You do get some additional hardening from the radiation. But after a certain dose, it turns around and the material gets softer. So you harden and then it gets softer. And it's getting softer because you're dissolving the you're dispersing the precipitates. Two things. You're disordering the precipitates, but generally most of this happens at a very low dose very quickly in the first couple of dPa, but this thing takes a lot longer. But anyway, so you've got two things going on here now. You've got some hardening from radiation damage, cluster formation, but you get some softening from disordering, but it's all happening here. And then with extended time, you get some dissolution of the precipitates. And what you'll notice here is that the lower irradiation temperature, that the softening is more prevalent. And that's because this process here happens more readily at low temperatures. It happens more readily at low temperatures because these precipitations, there's another process going backwards. The thermodynamic process wants to reform these precipitates. At lower temperatures, that is a slower process. So for a given irradiation, two temperatures, you've got an irradiation effect dissolving these precipitates, dispersing them, ballistically mixing them. But at the same time, you've got a back process which happens faster, at a higher rate, at higher temperatures. And what that means is that you end up with more precipitates here than you do here at lower temperatures. So let's talk about the embrittlement. Here's a fracture surface of Inconel 600, just as an example to show the intergranular failure of this material. Now, I think this material probably wasn't heat treated to create carbides on the grain boundaries or anything like that, because in fact that's bad in Inconel 600. You don't want carbides on grain boundaries, or if you do, you want to keep heating so you disperse the chromium or rehomogenize the chromium. Anyways, this is the fracture surface after material had been irradiated in that's the high flux isotope reactor at Oak Ridge National Laboratory, 650 degrees C to pretty low dose actually, 8 dPa, but it has 1800 APPM of helium generated. It was fractured at essentially room temperature, ambient temperature in the cell. It must have been 35 degrees C. Maybe it was a hot summer they had there in Oak Ridge. And then this is the surface, and you see this funny little network. And what that is actually is we have very large cavities, and there are little ligaments of material in between the cavities, which is this white stuff here. And what you can imagine is that this is an interface in the bulk, which is very heavily decorated by very large cavities. What's interesting is that here they're all very large, here they're very small. It's like a honeycomb thing. Anyway, when this material fails, it's like toilet paper. When you pull apart toilet paper, it breaks, it tears along the perforations. So this is perforations in two dimensions now. So if you have a bulk piece of material and you have perforations on one plane, it's also going to tear preferentially on that one plane. Okay, let's move on to OPEX from reactor component. That OPEX is operational experience. I told you about Inconel 600. It's used in flux detectors. Here's a bit of OPEX from the Bruce reactor back in 1985. This is one of my first jobs when I was first working for Atomic Energy Canada, was to do the examination of a failed flux detector. They thought it was, some guys thought it was stress corrosion cracking. And where's the stress? I don't know. And these things are supposedly encapsulated in helium. So where's the environment? Where's the corrosion? And in addition, they weren't said everything was wrong about stress corrosion cracking. Some other people thought it was nitric acid attack, because these things had Inconel 600 is susceptible to nitric acid attack, and you can get nitric acid formed in areas where you have a high gamma field, because of the ionizations of the air. If you have moist air, you can get reactions between the nitrogen in the air and the breakdown of the free radicals from the water in an ionizing environment, and actually get nitric acid, HNO3, and that attacks elements. Anyway, irrespective, it wasn't nitric acid, it wasn't stress corrosion cracking, it was something, because there was no stress. These things, when the reactor starts up, the whole reactor vibrates. These flux detectors, which are critical for the shutdown systems, the safety shutdown systems of the reactor, these things just rattled themselves apart. Similar event, this was 600, I thought it was 625, was Inconel 600 in, I think that's wrong, that should be Inconel 625. In a PWR, was these, again, there was a flux thimble, a flux detector type device was being removed for maintenance in the Surrey reactor. They were pulling it out reactor, and it shattered. It shattered into 6 pieces. Again, scary stuff. And then in our own Candu reactors more recently, in the last 10 years, our Inconel spacers that keep the pressure tube separate from the calandria tube, if you remember the lecture on zirconium alloys, these things started failing. This is an OPEX now from about 15 years ago. The unirradiated maximum loads of the unirradiated material are higher than the maximum loads of the irradiated optimized spacer. So what that smacks of, remember here, is this going on. This point is lower than that point. So this was showing up like 10 years ago. So where we are with this now, with the spacers in the Candu reactor, is that these things are really brittle. The unirradiated loads are a lot higher than the maximum loads of the irradiated spacers, because we're getting weaker and weaker with time. And what do these things all have in common? Nickel, high nickel. So as I said, in steels, we only have 10% nickel. So if you're dealing with steels or any component containing nickel, you have to scale the the effect of the nickel accordingly. So the 7 times as much nickel, this is 8% now, in a nickel alloy than there would be in a conventional steel. Candu reactors, they have locations where springs are located. Inconel springs here for tensioning guide tubes, for control assemblies, for for reactor control, safety systems, either shutdown or whatever safety systems. The guide tubes are, you don't want them vibrating in the reactor, so they're generally installed with some tension. As I mentioned, flux detectors that go through the core, these monitor the reactions that go on, and they monitor the gamma flux, which is a function of the neutron flux in effect. So they monitor the power of the reactor. So they're monitoring the power reactor at different zones, and they're typically built using Inconel. And then we have these spacers that separate the hot pressure tube from the calandria tube. So these are important parts of the fuel assembly. So these things can be taken out after when they fail, or after 5 or 6 years or 4 years when they will fail. These things can't. They're in there forever. So there has been more concern over the last few years on the degradation of these materials. Now these things operate in these springs, tensioning springs, operate in the moderator outside of the reactor core, and the temperature here is low, 60 to 80 degrees centigrade. So we generally don't, so this is where temperature helps. At this lower temperature, those kind of the degradation mechanisms, which are so obvious at higher temperatures, embrittlement, doesn't apply when it's 60 degrees centigrade. These things are operating at 300 degrees C, they become brittle. So here's a spectrum for the Candu reactor for these 3 particular locations. The green here corresponds to the flux detectors, as you can see, and then the red corresponds to the spacers, and the blue corresponds to these guide tube tensioning springs. The thing to note is, whereas these things are always, the fast flux is dropping, going from this to this to this, the thermal flux is high. And in fact, in this particular case, the thermal flux for these is higher than it is in the core. I don't think this is right. I think this is just outside of the core. This is a bit of an exaggeration. They're all comparable, we should say. So what happens to our flux detectors? What are we looking at? Embrittlement. There's a spacer, Inconel spacer, surrounding a hot fuel channel. Insulating gas gap that separates the cooled moderator from the hot pressure tube. It would be bad if this pressure tube contacted this cold calandria tube, cold being 60 to 80 degrees centigrade, because that would cause hydride to precipitate where the contact point was, and that would be bad because then you get hydride blister formation, and then you get failure, and there have been locas. I mentioned the one in 1983 in the Pickering 2 reactor. It was channel G16 that failed back in 1983, before you guys were born. And no, yeah, maybe 1983. Man, yeah, that's a good point. Might be before you were born. I don't know. Anyway, you'll be too young to know. But there was a contact between the pressure tube and the calandria tube, and hydride precipitation formed, and eventually the whole thing burst apart. And there was this loss of coolant accident, something that's much to be feared in the nuclear industry. That happened. So having these spaces in position and intact is very important. But about 10 years ago, I would say 10 to 12 years ago, it became apparent that these spaces, the Inconel X750 spaces, were becoming really quite fragile, quite brittle after they were removed from service. So we're only subjecting them now to about 50 or 60 dPa, which shouldn't really make them that brittle. But after about 50 or 60 dPa, what was observed is that if you looked at the unirradiated material, it would fail in a kind of ductile manner. You might get some these little dimples that you see here. They nucleate on little carbide precipitates and stuff like this. But generally, it's tougher and it takes a lot to fail it. But the Inconel spaces, they were failing very brittle and very easily. So this one in particular was broken just by using your hands. It wasn't actually using your hands, using the manipulators. So manipulators in a hot cell, you could break these components. And actually, I have a video. I should have shown it, showing breaking of the spacer with the robot arms, if you like, or the manipulator arms in the hot cell. So these manipulators in the hot cells, if you're familiar with hot cells, they're not like RoboCop. They just have as much strength as you could impart with your own hands. It's just in the hot cell. So if you could grab one of these things, you'd die, of course. But if you could break them with your hands. So the fracture characteristics of the irradiated compared to the unirradiated material was brittle intergranular and ductile intragranular. So what we're building up here with all this OPEX, going back here, with all this OPEX, is a general trend is being observed. When it comes to Inconel alloys, I've chosen one here, Inconel X750, intergranular embrittlement is a common feature. So it's nickel that is important, because we don't see the same types of fractures with zirconium, for example. And that means, and as you probably remember from some of my some of the earlier lectures, we talked about zirconium and what was good about zirconium. Zirconium was good because it didn't absorb thermal neutrons, which is good because you don't get some of these reactions happening. But also, even at the high energy neutrons, zirconium has a very low N-alpha reaction cross-section. So on 2 counts, you're unlikely with zirconium to get any helium produced. So this nickel effect is doubly important in a Candy reactor, because in a Candy reactor we have 3 times as many thermal neutrons as you do in a PWR or a BWR. So again, I'll repeat it again, because the Candy reactor is operating with natural uranium, there's not as much fissile material around. So you have to compensate for that by having a very high thermal neutron flux. You have to have a lot more of the material to stoke the fire, if you like. The low energy thermal neutrons, you have to have a lot more of them around in order to maintain a criticality, to maintain the reaction in the reactor. So even when you have all these two processes, you have high thermal flux and nickel, there is one saving grace. Temperature is important. I mentioned how those springs, those tensioning springs, were operating at 60 degrees C, and they're not failing. Where am I got? I've lost these springs, and they're not failing. And I think one of the reasons for that is because it's a low temperature. So temperature is important. And dose is also important. If your material is not in there for very long, because there are nickel alloy Inconel components which are in fuel assemblies, for instance, in PWRs and BWRs, there are springs to keep the assembly together. There are spacers. There are a number of different parts of fuel assemblies which are actually made from nickel alloys. Although most of the fuel itself, the material around the core is made with zirconium, other bits of the assembly are made with typically Inconel. But if the Inconel isn't in the fuel assembly, isn't in the core for very long, it's only in there for 3 or 4 years, 4 years say, 4 to 6 years, some of them, let's say 4 years, doesn't really matter because you're pulling it out, big deal. It's like the flux detectors. Well, they fail after 5 years, we just pull them out, replace them. So the industry was never geared or inclined to worry too much or even to be concerned about embrittlement of nickel alloy components. Certainly the US industry, because they didn't have the nickel alloy components in any major structural components that had to survive for very long. There were specialized minor components in assemblies which, like fuel assemblies, which weren't in the reactor for very long. But in the Candu reactor, we have some critical components which are made from this, and they have to be in the reactor for the duration. And helium embrittlement is the big deal. So why is helium important? So here's just an example, show voids that form in a iron chrome nickel alloy. In this particular case, this is a ferritic martensitic steel, I think, to radiate at a high dose, high temperature, but with ions and self ions. So this will be with ions, Fe. So you're irradiating this thing with ions, and of course you're not going to be producing any helium. You have all the right conditions, in this particular case 500 dPa, 450 degrees centigrade, for whatever reason, to nucleate these cavities. If you remember the lecture last week, we talked about that the cavities would not normally be stable, but I'm sure nobody knows exactly why these things form and grow. There are some oddities, but the observation is that you get these cavities, they're large, and you get large amounts of swelling. In an ion irradiation case, you don't have any helium, and you'll look at the boundary, the grain boundary. Grain boundaries are nice and clean, nothing on there. So that's saying that all the point defects that arrive at the boundary are just simply absorbed. But you'll get interstitials and vacancies going to the boundary, so you don't get necessarily any odd structures formed around there. It's a nice recombination site. But when you have helium, the helium can get to the boundary, and when the helium's at the boundary, it'll stabilize vacancies, vacancy clusters, and you do get this higher concentration of helium along the boundaries perforating. Now, it's not that much different from the bulk, but it certainly is, because you can see this line, you can trace it, and that just tells you have a higher concentration along there. So cavities do not form on grain boundaries in the absence of helium, but they do when you do have helium. So vacancies which form cavities are absorbed by grain boundaries, but not when helium is present. So I showed you that fracture surface. Here's some TEM. One of my students, or employee students, for his PhD, was examining the with TEM, looking at this, what was going on, and that's why we know we have this. And they, with a focused ion beam, were able to cut out small TEM specimens at a crack tip. And then when you look at the crack tip, you see where the crack is going, and it's going along the boundary where you have the helium bubbles. You see it here in a mode where we see the element composition. There's this chrome carbides here. We also have titanium carbides, but they decorate the grain boundary, and the cracking occurs along the boundary and also along the interface of these precipitates with the alpha phase, which also is a grain boundary. Somewhat similar observations have been made in steels. Actually, this was made before we made our observations on Inconel, and in fact it was this evidence that prompted me to go to COG and say, we have to get some money to pay for doing some TEM to look at the look what we have in Inconel in our spacers. It was seeing this and seeing this. This was the intergranular failure. So this was about, when was this? This was about, this isn't 2005, this is 2005. Anyway, it was the late 2000s, around about 2007, 2008 was when I saw this and said, oh, maybe that's what's happening in our case. So actually, we didn't know that we had this kind of failure until about 2008, 2009. So this only became an issue. In looking back, we saw that the steels, they'd had this kind of intergranular failure. And you may remember I said, well, you could get this ductile failure if you had carbides decorating the grain boundary, and it might look like it's failing along the grain boundary, but it's still a ductile failure. But when you look at it, in this case, they don't have carbides on the grain boundary. What they do have is that they have these segregation of bubbles. In this case, they call them bubbles. And in this case, in the steel, although it's only 12% nickel, for the conditions that they were talking about in a PWR, 315 degrees centigrade, 70 dPa, they had 625 atomic ppm of helium. And that clearly is enough to get some segregation at the boundaries. And clearly that's enough to change the failure mechanism so you get this intergranular failure. The question is that because of this? I think highly likely. So let's look at our case in the Inconel and what mechanical test data we have to characterize our spacers in the CANDU reactor. You probably remember this again from one of the earlier slides. I talked about in the case of zirconium how creep of the fuel channel, the pressure tube here, is important because the pressure tube expands and it makes a gap between the fuel bundle and the and the pressure tube, and you get coolant flow that bypasses the fuel bundle. We want the coolant to be going past all of the fuel bundles to be cooling them. We don't want it to go bypass them. Anyway, this isn't about that now. We've moved on from everything you need to know about zirconium, which is the pressure tube, onto Inconel. And in the Inconel case, we're interested in this component, which is our garter spring. And it is a spring. It's a garter spring because it has to roll. It has to allow free passage of this tube inside the concentric tube, which is the calandria tube. So these tubes have to move one with respect to the other. And the best solution to avoid galling or anything else that would interfere with this free movement, the solution was to make this separator a spring. And in the case of the first springs that were in use, which were Inconel springs, their design was a loose design and they moved very easily. And also there was concern if it was a easily deformable material, it might yield. And when you put a low yield point spring on this, there's a chance you may stretch it during installation and actually cause plastic deformation, stretch the spring, and it wouldn't be tight on the space on the pressure tube. The thing that reactor engineers were very concerned about, especially after the LOCA that happened back in 1983, before you guys were born, was the fact that if these things were loose, they could move. So in the late 80s, they said, okay, our preferred spring material is Inconel, because that's a really good spring material. Inconel X750, that's a really good spring material. It's going to be tight and it's going to stay in place. And it's going to roll and it's going to do all the right functions. Unfortunately, even though this was about 87, nobody had read Larry Greenwood's papers. And if they had, somebody would have said, maybe you shouldn't do that. Okay. Now, at the time, I was young and innocent, and I wasn't even aware that this was happening, that they put Inconel. I think wasn't until 2000s that I became aware of the fact that some reactors were actually made with Inconel. Okay, with these spaces were actually Inconel. Anyway, so what's the interesting feature? One of the interesting features is that these spaces go around the pressure tube. So the pressure tube is hot, the moderator is cold. So where the spring is pinched between the pressure tube and the calandria tube, the moderator, it's cold, it's cool in the pinched zone. But everywhere else is hot. And it's hot from the heat from the pressure tube, but also you got nuclear heating. You got all these processes I was talking about because nickel has a high reaction cross-section. It's absorbing neutrons, it's producing NPs and N-gammas and all kinds of things. And all of this contributes to heating up this spring relative to the other stuff around it. So you've got the heat from the channel, and you've also got the fact that it's self-heating. Some of our engineers did finite element calculations of the heat flow in the assembly, and this is the kind of temperature distribution you might find around the spacer. At the top, the cold bit is the temperature of the pressure tube, and above that, slightly hotter because of the nuclear heating, the self-heating, and there's kind of the reverse happening at the bottom. Except at the bottom, we've got this. It's sandwiched between the pressure tube and the calandria tube, and the average temperature is somewhat lower. It's somewhere between this temperature and this temperature. So we typically say it's around about 200 degrees C or 180 degrees centigrade. But of course, there's a temperature distribution. So you have to be careful when you're testing. What are we testing? Are we testing the hot bit or the cold bit? Okay, so when these things were took out of the reactor and tested, we put them in a load frame between some platens, applied a load, and they failed. So this is the unpinched, the hot one. This bit failed, broke apart. 55 dPa, but look at that, 18,000 ppm of helium. Remember me showing you this one? 625 APM of helium, and you're getting that. And these guys are worried about, well, it's a flux thimble, so you don't have to worry too much about it because you can replace it. But we can't replace this. And we have 18,000 APPM of 55 dPa, and that's only about half, just past halfway through the life of the reactor, life of operation. And if the thing was breaking up like this when you're crushing it, that's a bit worrying. And in the pinch zone, a little bit less helium. For some reason, I can't remember why. Oh, this is a different dose. Yeah, this is just a different dose, and the helium is proportional, roughly. It's not linearly, but it's roughly proportional to the dose. And in this shows the crush test, same type of facility, crushing, and it doesn't really deform in quite the same way. And these are the crush test results. We have an applied load, and in this case, the load is divided by the number of coils. So you're spreading the load over a number of different coils that are holding up a platen here, which is pressing down, crushing the spring. So when you divide up that load by the number of coils that are supporting it, you get a value, which is the applied load in terms of neutrons per coil. And this is the displacement. So it's only a small displacement. So you're crushing these loads, and the operating load in a reactor, like from the weight of the fuel, is about here. It's about 33, down here. So when you're in the irradiated case or even the unirradiated case, we're way above the operating load in the reactor. But now look what happens. So what happens here is after low dose, it hardens a bit, get a little bit reduction in ductility. But when you increase the dose and go further, depending on where you are, if you're at the hot bit or at the cold bit, your ability to support the material before it fails, it decreases. There might be a little bit of yielding here, but then it fails. So radiation hardens it as it would conventionally at low doses, but eventually, because of helium just keeps going. Radiation might saturate after a certain time, but the helium's going to keep going. So you may get some softening as well because of the dispersion of the gamma prime precipitates. But this is what's happening, and we're driving down towards this limit, which is worrying. I mentioned about the assembly, the window, the Inconel 718 window that was in the Lance, the accelerator for production of tritium facility, that had a yield, the strength behavior, the yield strength went up with dose and then came down, and we see exactly the same thing with our spacers. What's interesting here, we see the same temperature dependence as we did with the Lance program. So what we see with our Inconel X750 is, well, no, it's happening the same. It's consistent with other precipitation hardened nickel alloys. That's good. At least we know that. Regulators are always very happy to hear that kind of thing. the fact that you understand it. That's the most important thing. I think the worst thing a regulator would want to hear and would balk at is researchers, materials engineers, reactor engineers coming and say, oh, we see this or we see this, but we don't understand it. Even if you're way above the operating conditions, for instance, let's say in terms of load or whatever, even if you're way above that, the worst thing you can do is say, we don't understand it. If you understand it, that's fine. So again, we have this process going on with this decrease in the yield strength. In this case, determined from microhardness. So the hardness of the material is a surrogate, is another measure of the yield strength against dose, dPa. Oh, so I've talked about that, and I'll labor this again a little bit. I talked about the precipitates, and I talked about, but let's talk about other things that harden the material, clusters. In this case, we have some very obvious clusters, which are these cavities. So this is what the cavity structure looks like in the pinched region, in the low temperature. And this is what it looks like at high temperatures, in the unpinched region. As you might expect, it's coarser a little bit. It has some structure, kind of like galaxies, where they have this network structure. This is the infinitesimal opposite of the infinite, which is our I'm getting on tangent here, with what you see with the galaxies. They have these cosmological things, structures, pictures of how galaxies are arranged in a network in the universe. Well, this is the infinitesimal opposite of that. At low temperatures, it's a much more uniform structure. When we first had this phenomenon, when we were first aware of the amount of helium being produced, 18,000 atomic ppm of helium, we commissioned guys at Oak Ridge to do some modeling, and the modeling, cluster dynamics modeling, showed you what you expected, and you get the same kind of size, average size production of the helium cavities, bubbles they would call them, and then high temperatures, this is what you get. And that just, again, that's all good fodder for saying to the regulator, oh, we know what we understand this because we can even model it. But there's some other interesting features. You remember in the lecture I gave about diffraction and use of TEM and X-ray diffraction to characterize the microstructure of materials. Well, here's using TEM imaging, TEM diffraction, contrast now, to look at the dislocation structure inside the material. Now, the kind of fuzzy areas here are actually the contrast from the cavities, but the darker stuff is actually dislocations and dislocation loops. Now, the dislocations are already in there from the production, from the fabrication. So that's in here. But in this particular, if you notice, this side is different from this side. This is very much cleaner than that. And that's because this contains also a large fraction of these little black dots, which are really interstitial clusters, radiation damage. So we have this cluster damage here and very little evidence of it here. So intuitively, this is going to be harder as well because of all this extra stuff in there, in addition to the normal cold work dislocations. And in this case, we have cavities. In this case, we have cavities. In this case, we have cavities and radiation damage as well as the dislocations. And what's happening with the precipitates as a function of temperature? Well, there's our little precipitates in the unirradiated case, but what happens when we irradiate? Well, we have these collision cascades that happen. At this kind of time frame. We'll have a cascade event in this frame of view. Let's say we're looking at this in real time. We have to wait a couple of hours, maybe. Oh, there's another cascade event. And this is the kind of scale, this is the kind of thing that's happening in real time in a reactor. It takes a while, and then eventually there'll be another one. It's not boiling around. It's things are happening on glacial scales. It's like a geological time scale that's happening. But these very cataclysmic events that are happening at a very, very at the atomic scale, they're only happening at a very lazy pace, if you like, in real time, and it's the eventual build-up of these events, which seem very gentle in at any one instant, but cumulative over 20 years, this all builds up. Depending on how much of this heals, this all builds up to eventually create some change in the microstructure. And the neat thing about the helium that's produced from all these events, it doesn't go away. You can't heal that. You can't do anything with that. So what happens is that you get these collision cascades that come in from these very high energy events, or from the N gamma events, or from the NP events, or whatever. There's all kinds of different processes that are going on. And this all adds to eventually dissolving these particles. So you get this radiation dissolution. But at the same time, there's a thermodynamic driving force to reform this gamma prime. And the reason it formed in the first place is because it was the equilibrium state of the material when you heat treated it, when you did the spring temper to create. Spring temper is at 700 degrees C, of course, but at 700 degrees C you have a high enough temperature and enough diffusion that you'll get these formed very readily at temperature. At 300 degrees C, this reformation process is going to be very much slower, such that this other process, this damage process, which is also glacial and happens at a very slow pace, in effect, even though you might get every atom displaced once a year, or twice a year in this case, the fact that this is a slow process and this is a slow process, it's the balance of the two. And what happens is that at high temperatures, you still have some residues of the original precipitate structure apparent, but at low temperatures, it's pretty well dissolved. So the gradual decrease in the yield strength and the temperature variation can be explained simply by this process. So when it comes to what is the effect on the mechanical properties, 143, we have this nice plot where this guy Lee, in I think about 3 or 4 years ago, came out with an article in JNM where he plotted the strengthening factor. We didn't spend too much time about strengthening, other than to say that any clusters, any precipitates, things which are a barrier to dislocation slip will strengthen the material. I talked a little bit about the strain aging effect and the precipitate size. Well, the same thing applies with other types of clusters. And then often it's not just the size of the precipitate, it's the spacing, obviously, between the precipitates. But for a given precipitate type, there's a thing called a strength factor, alpha. And that dictates that all of the factors being considered: the size, the spacing, and by that, the number density. So really the size and the spacing. How much easier or harder is it for a dislocation to get by a precipitate, or sorry, a cluster of it, and that factor is given by the strength factor. So in this case, we're not considering the effect of thermal aging as you would when we discussed precipitates, and how when you age an alloy and you're doing some precipitation aging, that the precipitates get bigger. When they get bigger, they're also getting further apart. This is more about just simply the size effect of the precipitate. So when they're smaller, it's easier to, if you like, cut through a precipitate, spherical precipitate. It's easier to cut through cavities. It's easier to cut through, to cut through loops and stuff like that, and other things. And as they get larger, it becomes harder. So this would be on that. If you can cast your minds back to when we looked at the R1 looping and the cutting, this would eventually be bypassed. As in the case of precipitates, we'd get to a point when the precipitate size gets so big when you're aging that the spacing gets so big that the dislocation can bypass and go in R1 looping. And at that point, in terms of the precipitates, they'd go up to a certain point and then they'd come down, simply because this would correspond with an aging, also the spacing of the precipitates. In this realm, for this case, for this study, I'm pretty sure that this is just simply the size factor, irrespective of any spacing between the precipitates. So it's only the size factor that matters, and for different types of defect. And here what I put on is where we would sit for all these strengthening factors if our spacer is pinched at the low temperature compared to unpinched at the high temperature. So it makes sense that everything considered, whether it's the damage density or the lack of precipitates, or lack of loops, or the dissolution of the precipitates, or the size and the distribution of the cavities, in terms of the strengthening factor of these components within the microstructure, in the pinch material, it's always at a low strengthening factor. So the lower yield strength can be attributed to a number of different things, but mostly I think it's the dissolution. It's the dissolution that is the most important. Oh yeah, and the reason that this is the most important is because this is the one that's in terms of numbers of cavities, we're increasing them. Numbers of small precipitates, we're increasing them. The number of dislocation loops, these are all going up with dose, with increasing dose. The only thing which is in terms of going down this way, the only thing which is enhanced by increasing dose is the dissolution of the gamma prime. So that's why over a long duration we have the drop in the strength of the material, the yield strength. It's becoming softer, and it's attributed to the dissolution of the gamma prime. Okay, we talked about the embrittlement, talked about cavities being along the grain boundary. This is the first picture that was ever taken of the cavities on the boundary when we first knew that we had this perforation effect to contend with. I took this. Even though I was a manager at the time, they couldn't get the microscope focused. So they called me over into another building and said, we don't see anything. And I said, well, let me look. And I spent half an hour focusing the microscope, not focusing it, aligning the microscope so that you could generate images like this. So why are these cavities? Why do we have this perforation? Makes it easier to deform along the boundary? Well, one of the obvious things is that the closer the particles get together, the more area we have of the boundary that's covered by these particles, then the stress intensity between the particles goes up. So even though you might have a standard applied tensile stress, the stress intensity between the particles is a function of their the ligament distance between the particles. So to some extent, yeah, it makes sense that the material will be more weaker when we have this kind of structure. One of the things I did in my last couple of years, just shortly after I retired, was to do some modeling, and this is the modeling using rate theory modeling now of the cavity buildup along the boundary. I'm not going to talk about it too much, but this is another thing where the regulator gets happy, or certainly the reactor operator's happy. Can you model it? And in that case, they wanted to model it because they were concerned, because what they didn't want to see was this thing going up. They wanted to make sure that the models, in terms of projecting out to the future, weren't showing that it was going to be a curve, an increasing curve. That the deposition rate of both the helium and all the point defects, the atoms and vacancies, and all the net effect of all the fluxes of all the point defects that come to the grain boundary, they wanted to see that the net effect is that in terms of this bubble area coverage, that it was dropping and not going up. And I was able to do that, and that's great. It's kind of very loosely related to the TM observations. These are the TM data, but the TM data themselves are scattered, so who knows. But the main thing is that any modeling, or what's going to be the main factor which dictates the strength, is the weakest, the worst limit. So what you really want a model to do is to be conservative, to be on the edge of this distribution of the observations, to be on the edge of the observations. So in the end, you can build up a picture of what's happening to the material with time in the reactor. Let's just think about it in terms of true stress, the stress let's take a chunk of material and look at the true stress and look at what's happening with time. Well, with time, the yield strength, depending on the temperature, at high temperatures first increases and then drops down according to this precipitation dissolution we're talking about. At lower temperatures, you get more dissolution, and so it's a lower value. This represents the yield strength. This represents the upper tensile strength, which you would normally achieve in a normal tensile test. You yield and then you fail in the ultimate tensile strength. And then this represents the grain boundary. So normally the grain boundary is the last thing to where failure would happen. However, if the tensile strength, because of strain hardening, went up above this, eventually the grain boundary, you may fail, especially if you have those carbides on the boundary and this kind of thing. But let's not worry about that for now. Typically, the grain boundary has a higher strength than everything else. It's the last thing to fail. So if you didn't have carbides on the boundary, the boundary would be pretty strong. So let's pick a time. Early on, 5 years reactor operation, material yields, and then it fails, but it's in the ductile region because you don't have anything on the boundary to worry about. And certainly the material, there may be some carbides here which are nucleation sites for ductile dimples, whatever, but there's not sufficient to, most of the failure happens in a ductile manner, not necessarily at the grain boundary in this particular case. Now we go to a higher dose, again, the material yields at the yield point, and then it fails. But we don't get to the point of what would normally be the ultimate tensile strength. It fails at the grain boundary because the grain boundary strength is dropping. And why is it dropping? It's because we keep decorating it with helium, perforating it with helium bubbles. And this is the point of concern, is do we just get to a point where the material just fails? And that is not desirable in any reactor application, because that's essentially saying we have glass in there. We have zero ductility, and our major component that is holding up our main fuel channel is like glass. Okay, we've got a few minutes now. The last thing I wanted to talk about, I mentioned those tensioning springs that are operating at a low temperature, 60 to 80 degrees centigrade. So we don't really have to worry about their strength and in terms of their fracture behavior, but they have another function. In this case, it's the tension. It's the tension of the springs. They're torqued down so that they apply a load, a tensile load, on the fuel assembly. On the guide tube. So the ability to maintain a load, a tensile force on a component for some springs, for tensioning springs, that is important as well. And what happens during irradiation or operation of the reactor is you get detensioning. We get a relaxation of this force. And so we get a relaxation of the force. And this is called irradiation enhanced stress relaxation. So to distinguish it from the other types of radiation enhanced stress relaxation, sunbathing, going to sleep in the nuclear reactor control room, this is a different type of stress relaxation. So this is the type of stress relaxation that happens when you apply an elastic stress on a material. It's below the yield point, so you're not yielding it. You're not creating dislocations. You're not fracturing the material. But if you sit it with this load for long enough, if you have a means of transferring mass, then the vacancies will go this way and the interstitials will go this way, because this part wants to elongate and this part wants to shrink. So in irradiation, we have interstitials and we have vacancies, so we can do that relatively easily. Now you can also do it thermally, because a vacancy would move from here to here and you'd get stress relaxation. Because if you take this load off after a time, this curvature would be frozen in, would be plastically retained. So stress relaxation is the conversion of an elastic stress into elastic strain into a plastic strain. And this transfer of elastic strain into plastic strain is enhanced by having point defects, by having an elevated concentration of point defects. So if you remember in the ray theory lecture, I said during irradiation, the number of vacancy point defects is elevated by something like 4 or 5 orders of magnitude. And the number of interstitial point defects is elevated by 6 to 8 orders of magnitude. So with irradiation, we have lots and lots of these point defects floating around. So long as they're mobile, and interstitials are very mobile, even at 300 degrees C, we will get some stress relaxation. And in fact, we'll get some stress relaxation even at low temperatures when the vacancies might be immobile, because the interstitials are mobile. Okay, so how did it impact the operation of a CANDU reactor? Well, during a routine maintenance in 2006, the reactor engineers were concerned because one of the adjuster rod guide tubes that they were looking at was relaxed. It was rattling. I mean, it wasn't under tension. I mean, they had to talk it. Well, I don't even know if they could talk it up, but they realized that it was relaxed. It wasn't doing its function. Now, it turns out that this was a concern, and the regulator was very concerned about this because here was something that wasn't supposed to happen. So even though it wasn't a big major event in terms of, it was something that, hey, this has been, we've had this thing in operating in the reactor for 18 years, but by our previous calculations, it shouldn't have relaxed. Remember me saying regulators, the one thing they don't like is people say, oh, we don't understand that. So let's go a little bit further back into what's the story, if you like. So these things are, they have this little, this is a locator, but this assembly, they have a means of this rod somehow pushes down on this spring, and this spring pushes down on this tube on the outside. I think that's how it works. And what it does, it applies a tensile force to this outside tube here, and it puts it in tension. So this thing pushes down on that, this thing pushes down on that, and we have this tensile force. I think that's how it works. Anyway, in order to compress it, they have a little nut at the top here, and when they first installed the reactor, it's adjusted to an actual load of 1,400 pounds. I guess that's 1,400 pounds weight. Yeah, which to me is a lot. So you're really pulling down heavily on this thing. And the temperature is low, 60 degrees C. So, you know, they wouldn't really expect much relaxation thermally over the life of the reactor. So any relaxation because of that diffusional mass transfer that I talked about is likely to happen because of radiation creep. Now, it just so happens that there were some creep tests conducted at Chalk River and NRU reactor. And you probably remember earlier on in this lecture I said about how many people used fast fluents. I should have said this is, I realize this is not very well. This is fast fluents. This is neutrons E greater than 1 MeV. E greater than 1 MeV. I've added the displacements per atom here, but when this data was first used in anger, it was only the fluents. People hadn't bothered to do the displacements per atom because to a large extent, especially for zirconium, the fluents are proportional to the dose. Sorry, to the displacements per atom. And even also in Inconel at early times, maybe, but not actually. Maybe I shouldn't say Inconel. I've let the cat out the bag there. It's a presumed presumptive thing. Anyway, I shouldn't have mentioned that. But even in steel, for instance, even in chrome or iron or copper, you know, the displacement per atom is roughly proportional to the fast fluents. This is the fast fluents now. So they had these results, and they said, well, okay, fast fluents, we've got about 90% relaxation after a fast fluence of 1 × 10 to the 25. So they look at the spectrum They look at the spectrum at the location of this flux detector here. We're right at the edge of the core of the reactor. Actually, the spectrum is very low. Sorry, the fast neutron dose here is very low. So they looked at that and said, well, how long would it take us to get to this fast fluence? 650 years. So they had an assessment for Gentil reactor, 60 degrees C, use this curve, use that fast fluence, find out how long it would take to get that fast fluence at this part of the assembly here, 650 years, don't worry about it. So I have a letter, when I was a manager, it was a letter written by one of my predecessors and said to Gentil saying, don't worry about it. But remember me saying about the regulator saying, well, it's completely relaxed. It's only been in there 18 years. We thought it would be good for 650 years. And that's the last thing you want to be saying to a regulator. So they have to understand it. That's the important thing. Why is this happening? Why is it completely relaxed after 18 years instead of 650 years? So one of the texts I got from when I was a manager, but I had this came across my desk, and the obvious thing was to say, well, what about gamma radiation? Because we're in a CANDU reactor, thermal flux, you're not absorbing many neutrons, you're going to have a higher gamma flux, in fact, at the periphery. So we talked about a little bit about gamma damage last week, I think, but I didn't go into it too much. But I think I did show you the presentations or the papers that talk about it. So you can do the gamma if you get the gamma flux from the reactor physicists, and you look up all the cross sections involved. This was difficult, I must admit. This was difficult. So back in 2006, I calculated the gamma damage at all locations along the spring. So these are all the radial locations along the spring. And there's the DPA rate when we calculate from the fast neutrons, and it's pretty small. This is divided by 10 to the minus 8 per second. So it's really quite small. It's 0.1 times 10 to the minus 8 per second. So that's a pretty low DPA rate, and that DPA rate is not sufficient. That would take 650 years for the spring to relax, and the gamma is not going to help you much. It's orders of magnitude. So one of the things I thought about at the time, what about the thermal neutrons? Okay. We put in the thermal neutrons. You remember me saying about a thermal neutron, when it gets absorbed by a naturally occurring iron 56 or nickel 58, there's this recoil when the gamma photon is emitted, and this recoil produces about 5 or 6 displacements. When you put that in the mix, because we do have a lot of thermal neutrons in a CANDU reactor, bing, there it is. I thought, well, there's the answer. Well, not quite, because including the thermal neutron effect, put that relaxation down to about 30 years. But we were up here, and the thing was completely relaxed. It basically wasn't sufficient. There wasn't sufficient damage to account for the amount of relaxation that we were observed. So it just so happened a colleague of mine, a guy called Frank Garner, called me for Christmas. It was Christmas time. How are we doing? Happy Christmas. Hey, I'm writing a book about nickel 59 or gamma. Sorry, he was writing a book about radiation effects on materials in reactors, and I don't have any entries about the CANDU reactor. Do you have anything interesting that I can put in the book? And I think it was about spectral effects, he was saying. And I said, oh yeah, I've got this interesting thing where, you know, I looked at the fast neutron damage, and then, well, when I included the thermal neutron damage, we got somewhere close to be able to describe the relaxation. And he said, send me what you've got. That sounds interesting. Sounds just the sort of thing I want to put in my book. And then he called back the next day and he said, what about nickel 59? So remember, Garner was on the paper with Larry Greenwood in 1985, talking about, in this case, the NP reaction with nickel 59. And I said, what's that? Anyway, he sent me the paper from Larry Greenwood, and I very quickly did some calculations with the nickel 59 included. What about nickel 59? And there's the relaxation. When you include nickel 59 in terms of relaxation, it drops from 30 years, even taking into account some aspect of the thermal neutrons, but with the naturally occurring nickel 58 isotope. Now we go add nickel 59 in the mix. It's relaxed after 3 years. Done. Anyway, very interesting. And it was a prime example. And then technical operability evaluation was written once we had that information. I didn't write that. The reactor engineers at Sheridan Park did that. But they were able to start the reactor up again. And the reason is not because, the reason was we understand it. Oh, we now know why it's relaxed. Then the question is, can we live with that? Yeah, we can live with that. The important thing was, did we understand it? Okay, so just to summarize, I've harped on about this. Power reactors are, because they have the thermal neutrons, you can generate a lot of hydrogen, helium, and displacement damage. A rule of thumb in a CANDU reactor, for example, after 4 or 5 years of operation, when you've built up a sufficient nickel 59, the displacement damage rate doubles with nickel 59. So whatever you had without considering nickel 59, it doubles in the reactor core. You might say, well, that doesn't sound like the same here. No, because here we have a very different spectrum. Here in the periphery, we have a much higher thermal neutron spectrum compared to the fast neutrons. The ratio of in the CANDU reactor, the ratio of the thermal neutrons to the fast neutrons right here is about 20,000 to 1. There are 20,000 thermal neutrons per fast neutron. Here it's about 3 to 1. Here it's about 3 or 4,000 to 1. So we have very many more thermal neutrons compared to fast neutrons here compared to here. So when I said that, in the core, it means a doubling of the displacement damage that you would get without the nickel 59. In the periphery, it's like 200 times as much displacement damage when you factor in the nickel 59. You get 200 times as much displacement damage compared to what you might expect. Oh, actually, not 200 times. That's wrong. It's actually 10 times. It's 200 times relative to the fast neutrons, and it's 200 times relative to the whole neutrons. But having said that, in the core, because the spectrum in the core, 90% of your damage is from fast neutrons anyway here, so it would be the same. It's just that in the periphery, 90%. 90% is from nickel 59, if you like. It just shows you have to take into account the spectrum wherever you are, and you have to be aware of nickel. So nickel 59 and nickel effects become important when you have a lot of nickel. But if it's steel and you only have 10%, then it's not so bad. And you don't have to worry about it quite so much. Anyway, there you go. Oh, nickel alloy components are susceptible to loss of strength, and that could create a loss of coolant, especially in the case of the spacers in the Candy reactor. And we're wrestling with that right now. So we're currently in the throes of refurbishing the Darlington reactors, and it remains to be seen whether the reactors will make it to their life management targets. Okay, thank you for listening, and I will sign off now. I won't sign off, but
we get it.
You get it.
Thank you very much, Malcolm. I really liked that brief history about how that nickel, I guess, concept was formed with the helium production.
Yeah, no, and you know what? Sorry, I'm just messing around. Yeah, it's not very academic, but I think it helps probably put things in perspective. Why would one why